Welcome to an in-depth look at the systems engineering challenges facing hydrogen aircraft design. Moving to zero-emission flight requires more than just a fuel swap. Designing a hydrogen-powered aircraft is not just about replacing traditional Jet A1 fuel, it demands a complete overhaul of the aircraft's fundamental architecture. Hydrogen aviation necessitates a fundamental architectural transformation, impacting everything from fuel storage to aerodynamics and structural integration. Why is hydrogen propulsion such a massive systems engineering challenge? It's because every design decision creates a ripple effect across multiple disciplines. Let's start with the first major design challenge: optimizing fuel storage and tank placement within the aircraft. Liquid hydrogen requires cryogenic, cylindrical tanks. This means fuel shifts from the traditional wet wings and moves primarily into the fuselage. This relocation profoundly impacts center of gravity management, changes structural loads, and redefines the overall aircraft configuration. The second challenge involves the critical trade-off between weight and volume for hydrogen fuel. Liquid hydrogen offers about 3 times higher gravimetric energy density than traditional kerosene, but crucially, it has about 4 times lower volumetric density. The consequence of this lower volumetric density is the need for much larger fuselages, resulting in increased wetted area and, ultimately, higher parasitic drag. Next, let's explore the third design challenge: optimizing aerodynamics in response to these structural changes. Changes to the fuselage geometry, necessitated by the fuel tanks, directly affect the aircraft's lift-to-drag ratio, which is vital for efficiency. These changes also require rethinking propulsion integration and its overall impact on aircraft performance. The fourth major challenge is dealing with the extreme environment of cryogenic engineering. Liquid hydrogen must be stored at an incredibly cold, -253 degrees Celsius. This requires meticulous boil-off management and careful handling of thermal stress. Engineers must contend with risks like hydrogen embrittlement and develop highly effective multi-layer insulation, completely redefining structural and materials engineering requirements. The fifth key challenge lies in structural integration and how the aircraft structure accommodates these new fuel systems. Hydrogen tanks are no longer just passive fuel storage. They must become critical structural elements, integrated directly within the airframe. This shift necessitates redefining structural load paths throughout the aircraft, ensuring integrity and performance while carrying the new fuel load. In conclusion, hydrogen propulsion is far from an incremental upgrade. It is a massive systems engineering challenge that touches nearly every aspect of aircraft design. The design touches aerodynamics, structures, materials, science, propulsion, flight controls, and, critically, the entire certification process. The future of sustainable aviation will belong to engineers who master these complex trade-offs. What do you think will scale first? Retrofitted tube and wing designs or fully optimized blended wing body aircraft?